Well, the universe is vast. It is older and bigger than we can truly imagine. Our home, the Milky Way galaxy, is just one of countless galaxies scattered across the cosmos. Inside our galaxy, there are hundreds of billions of stars. Many of these stars are a lot like our own sun. They have been shining for billions of years, providing steady warmth and light. And we now know that planets are not rare. In fact, they are everywhere. We have found thousands of them orbiting other stars. Scientists believe there could be trillions of planets in our galaxy alone. With so many potential homes for life, it seems almost certain that someone else should be out there. The numbers practically scream that we are not alone in this immense universe. So, where is everybody? This simple question is the heart of a profound puzzle. It's called the Fermi Paradox. It was famously asked by the physicist Enrico Fermi during a casual lunch conversation back in 1950. He did some quick calculations in his head. He considered the age of the galaxy, the sheer number of stars, and the possibility of interstellar travel. Even with very slow ships, a civilization could cross the entire galaxy in a few million years. That may sound like a long time to us, but on a cosmic calendar, it's just the blink of an eye. The galaxy is billions of years old. There has been plenty of time for many civilizations to rise, expand, and make their presence known across the stars. Yet, when we look up at the night sky, we see a profound and deafening silence. We listen with our powerful radio telescopes, but we hear no alien broadcasts. We scan the stars for signs of advanced technology, like massive engineering projects, but we find nothing. There are no alien ships in our solar system. There are no probes from distant stars visiting Earth. It's as if the universe is completely empty except for us. This contradiction, this strange and unsettling quiet, is the mystery we are going to explore. The universe should be teeming with life and intelligence, but all evidence points to a lonely existence for humanity. This paradox forces us to confront some of the biggest questions we can ask. Are we truly alone? Is life incredibly rare? Or is there something else going on that we don't yet understand? In this documentary, we will journey through this puzzle. We will look at what we know for sure, based on scientific evidence. Then, we will venture into the realm of speculation, exploring the many fascinating and sometimes frightening ideas that try to explain this great cosmic silence. We will separate the facts from the theories. By the end, we might not solve the paradox, but we will certainly understand why it is one of the most compelling questions in all of science. To get to the bottom of this puzzle, we need a clear plan. Our journey will be divided into several parts. First, we need to appreciate the true scale of our galaxy. We will start by exploring the Milky Way itself. We will talk about its immense size. We will talk about its structure. We will talk about the hundreds of billions of stars it contains. Understanding this scale is crucial. It's what makes the absence of evidence so strange. We will look at the different kinds of stars and how long they live. We will also discuss the habitable zone, that special region where a planet could have liquid water on its surface. This is the first step in building the case for why life should be common. Next, we will use a famous tool, the Drake equation. This isn't a strict mathematical formula with one right answer. It's a way to organize our thinking. It breaks the big question, how many civilizations are there, into smaller pieces. We will look at each part of the equation. How many stars are born each year? How many of those have planets? How many of those planets could actually support life? We will examine what science can tell us about each factor. And we'll be honest where knowledge ends and guesswork begins. After considering where life might arise, we have to think about the challenges of getting from one star to another. The distances are mind-boggling. We will discuss the limits of interstellar travel and communication. Even light takes years to travel between the closest stars, so how could a civilization spread across the galaxy? We will explore colonization ideas, slow-moving generation ships, and advanced, self-replicating probes. These models show that even with known physics, a civilization could fill the galaxy. That only makes their absence more puzzling. Finally, we confront the most speculative part: possible solutions. We will introduce the Great Filter. The idea, some barrier extremely difficult for life to overcome. Is the filter behind us, meaning we were lucky? Or is it ahead, a danger awaiting advanced civilizations? We'll explore hypotheses. Life is rare, civilizations destroy themselves, or we are being deliberately ignored. Join me as we weigh evidence and speculation and try to make sense of our place in the cosmos. To understand the Fermi Paradox, we must first appreciate where we live. Our home is not just the Earth, or even our solar system. We are residents of a vast, sprawling city of stars called the Milky Way galaxy. From our perspective here on Earth, it looks like a faint, milky band of light stretching across the night sky. Ancient cultures saw it as a celestial river, or a pathway for the gods. But with the invention of the telescope, we realized it was something far grander. That hazy band is actually the combined light of billions of distant stars. We are looking into the dense, crowded plane of our own galaxy from the inside. It's like being in the middle of a forest and seeing a thick wall of trees in every direction. The Milky Way is a spiral galaxy. It has a bright, dense center called the galactic bulge, which is packed with old stars. From this center, several long, graceful arms spiral outwards. These arms are where the action is. They are rich in gas and dust, the raw materials for making new stars. Our own sun and its family of planets reside in one of these spiral arms, the Orion arm. We are not in the chaotic city center, nor are we out in the quiet suburbs. We are in a comfortable, relatively calm neighborhood, about 2/3 of the way out from the galactic core. This location is important. It keeps us away from the intense radiation and gravitational disturbances of the galaxy's center, which would be hostile to life as we know it. The sheer size of our galaxy is difficult to comprehend. If you could travel at the speed of light, the fastest speed possible in the universe, it would still take you about 100,000 years to cross from one side of the Milky Way to the other. Think about that. A beam of light, which can circle the Earth more than 7 times in a single second, would need 100 millennia to complete a one-way trip across our galactic home. The galaxy is not just wide, it's also thick. The main disk of stars is about 1,000 light-years thick. Our galaxy is a colossal, spinning island of matter and energy, floating in the even vaster emptiness of intergalactic space. This immense scale is the first piece of our puzzle. A place this big, this full of raw materials, and this old, should have had plenty of opportunities for life to arise. It's not a small barren rock, it's a continent-sized petri dish, and the experiment has been running for billions of years. When we say the universe should be full of civilizations, we aren't just talking about the whole universe. We're starting right here, in our own backyard. The Milky Way alone presents us with a staggering statistical case. The paradox begins here, in the humbling, mind-stretching expanse of our own galactic city. Now let's populate our galactic city. How many stars are in the Milky Way? The honest answer is that we don't know for sure. We can't count them one by one. Many are too faint or too far away. Many more are hidden behind thick clouds of interstellar dust. But we can make a very good estimate. By studying the galaxy's mass, its brightness, and the types of stars we can see, astronomers have arrived at a number that is both awe-inspiring and foundational to the Fermi Paradox. The current consensus is that the Milky Way contains somewhere between 100 billion, 400 billion stars. For our discussion, let's just use the number 200 billion as a conservative middle ground. 200 billion. That number is so large that our brains can't really grasp it. So let's try an analogy. Imagine you have a large bag of sand. If you were to count every single grain of sand on all the beaches and in all the deserts on Earth, you might get a number that is in the same ballpark as the number of stars in the universe. But just for our galaxy, let's stick to a simpler scale. If you were to count one star every second, without ever stopping to eat or sleep, it would take you over 6,000 years to count to 200 billion. That's longer than all of recorded human history, from the first writings in Sumeria to today. Every single one of those stars is a potential sun. The stars in our galaxy are not all spread out evenly. They are concentrated in the central bulge and along the spiral arms. But even in the space between the arms, the distances are vast. The nearest star to our sun is Proxima Centauri. It's about 4.2 light-years away. That's more than 25 trillion miles, or 40 trillion kilometers. If you were in our fastest space probe, it would still take you tens of thousands of years to get there. And that's our very closest neighbor. The average distance between stars in our part of the galaxy is even greater. This vast emptiness between the stars is one of the great challenges for interstellar communication and travel, something we'll explore later. But for now, let's focus on the number. 200 billion potential suns. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. The numbers become astronomical, almost nonsensical. But let's stay home, in the Milky Way. If even a tiny fraction of those 200 billion stars have planets, and a tiny fraction of those planets are suitable for life, and a tiny fraction of those develop life, the numbers still add up. The law of large numbers suggests that rare events become certainties. This is the statistical power behind the Fermi Paradox. The galaxy doesn't just provide a few chances for life, it provides billions upon billions of them. Section 3. Stars. The engines of creation. Stars are not just points of light, they are the engines of the cosmos. Giant, churning nuclear furnaces. Deep inside their cores, under immense pressure and heat, they fuse lighter elements into heavier ones. This process is called nucleosynthesis. It's the source of their energy. It makes them shine for billions of years. Our sun, a fairly average star, has been converting hydrogen into helium for about 4.6 billion years. It has enough fuel to shine for another 5 billion years. That long, stable lifetime matters. It gives a consistent energy source for slow, gradual evolution on orbiting planets. The elements forged in stars are the building blocks of life and planets. Early universe, almost only hydrogen and helium. Every other element, the carbon in your body, the oxygen you breathe, the silicon in the rocks beneath your feet. Massive stars don't just fade, they explode as supernovae. These supernovae can briefly outshine a whole galaxy. In those final moments, they scatter heavy elements across space. This cosmic recycling is essential for life. Gas and dust enriched by exploded stars form vast clouds, nebulae. These are the galaxy's stellar nurseries. Over millions of years, gravity pulls material into dense clumps. Cores heat up. A new star ignites. Leftover disk material, gas and dust swirling around the newborn star, doesn't go to waste. This is what planets are made of. Our solar system formed from such a disk of recycled stardust. We are, literally, made of star stuff. The story of life is inseparable from the story of stars. A habitable planet can't be only hydrogen and helium. It needs a rich variety of chemical elements, so it must form around a later generation star, born from previous stars' ashes. Fortunately, our galaxy is over 13 billion years old. Plenty of time for many star generations to enrich the galaxy for planets and life. The chemical ingredients aren't rare. They're a standard product of the galaxy's life cycle. Section 4. The Stellar Zoo. From dwarfs to giants. Not all stars are created equal. When you look up at the night sky, the stars may seem similar, but they come in a wide variety of sizes, colors, and temperatures. Astronomers have a classification system that organizes this stellar zoo. The vast majority of stars in the Milky Way, about 75% of them, are small, cool, and faint stars called red dwarfs. These are the most common type of star in our galaxy. They are much smaller and less massive than our Sun, and they burn their fuel incredibly slowly. A typical red dwarf can live for trillions of years. That's far longer than the current age of the universe. Their long, stable lives could offer an enormous window of opportunity for life to evolve. On the other end of the spectrum are the massive, brilliant blue giants. These stars are huge, some hundreds of times more massive than our Sun. They burn through their fuel at a furious rate, shining with incredible intensity. But they live fast and die young, lifetimes of just a few million years, not billions. This is probably not enough time for complex life to get started on any orbiting planets. After their short, spectacular lives, they explode as supernovae, seeding the galaxy with heavy elements for the next generation of stars. So while they aren't good candidates for hosting life themselves, they are crucial for creating the materials life needs. In between these two extremes are stars like our Sun. Our Sun is classified as a G-type main sequence star, or a yellow dwarf. It's a bit of a misnomer because it's actually quite white, and it's certainly not a dwarf compared to the red dwarfs that dominate the galaxy. Stars like our Sun make up about 7% of the stellar population. They strike a good balance. They are massive enough to have a decent habitable zone, but not so massive that they burn out too quickly. Their lifetimes of around 10 billion years seem to be a sweet spot, providing plenty of time for planets to form and for life to evolve from simple microbes into something more complex. So, which stars are the best targets in the search for life? For a long time, we focused on Sun-like stars because we had one example of a planet with life, and it orbits a Sun-like star. However, the sheer number and incredible longevity of red dwarfs make them very tempting targets. Could life evolve on a planet orbiting a star that will shine for 1 trillion years? It's an active area of debate. These stars are prone to violent flares which could be harmful to life. But with 75% of the galaxy's stars being red dwarfs, ignoring them means ignoring the vast majority of potential homes for life. The stellar zoo is diverse, and it's possible that life could find a way to thrive in many different kinds of stellar systems. Section 5. Worlds beyond our Sun. For centuries, planets were just the wandering lights in our own solar system. The idea of planets orbiting other stars was pure science fiction. We had no proof. All of that changed in 1995 with the discovery of the first exoplanet orbiting a Sun-like star, 51 Pegasi b. This discovery opened the floodgates. It marked the beginning of a revolution in astronomy. Since then, we have confirmed the existence of thousands of exoplanets, and the number grows every week. We have found them using several clever techniques. One of the most successful is the transit method, used by NASA's Kepler Space Telescope. It involves staring at a patch of stars and looking for tiny, periodic dips in their brightness. These dips in brightness are caused by a planet passing in front of its star from our point of view, blocking a small fraction of the starlight. It's like watching a moth fly in front of a distant streetlight. The dip in light is minuscule, often less than 0.01%, but our instruments are sensitive enough to detect it. By measuring how much the light dips, we can determine the planet's size, and how often it happens, we can determine how long it takes to orbit its star. The Kepler mission stared at a single patch of sky containing about 150,000 stars for 4 years. What it found was astonishing. Planets are not the exception, they are the rule. The data from Kepler and other planet-hunting missions have fundamentally changed our understanding. The statistics suggest that, on average, there is at least one planet for every star in the galaxy. Let that sink in. 200 billion stars, and at least 200 billion planets. And that's a conservative estimate. Many stars have multiple planets, just like our own solar system. This means the total number of planets in the Milky Way could be 1 trillion or more. Our galaxy is teeming with worlds. We have found gas giants larger than Jupiter orbiting scorching hot close to their stars, super-Earths, planets about the size of Earth. These discoveries transform the Fermi Paradox from a philosophical question into a scientific one. We are no longer guessing about whether other stars have planets. We know they do. We have the data. We have the catalogs. These worlds are no longer theoretical. They have names like Kepler 186f, TRAPPIST 1e. We know their sizes. We know their orbits. The first term in any equation for life in the universe, the number of planets, is huge. The galaxy is a vast cosmic ocean, and we now know it's filled with islands. The question is no longer, are there other worlds? The question is, are any of them like ours? Section 6. The Goldilocks Zone. Not too hot, not too cold. Having a planet is just the first step. One of the most crucial ingredients is liquid water. Water is a fantastic solvent. It enables the complex chemical reactions of life. Life on Earth is completely dependent on it. So we ask, could the planet have liquid water on its surface? That depends on the planet's temperature. And temperature depends primarily on distance from its star. Get too close, water boils away into space. Get too far, water freezes into solid ice. There is a just right region in between. The circumstellar habitable zone, the Goldilocks zone. The orbital band where temperatures allow surface liquid water. Not too hot, not too cold. The size and location depend entirely on the star. Sun-like star. Habitable zone sits where we expect. Earth is comfortably inside the sun's zone. But being in the zone doesn't guarantee water. And it doesn't guarantee habitability. Venus sits near the inner edge. Venus has a runaway greenhouse effect. Surface temperatures hot enough to melt lead. Mars sits near the outer edge. Mars is a frozen desert with a thin atmosphere. A planet needs more than just the right location. It needs the right size to hold an atmosphere. It needs the right atmosphere to maintain stable temperature. It needs the right geological activity. The Goldilocks zone is a starting point, a first-pass filter. It helps us pick promising candidates from thousands of exoplanets. Despite caveats, the concept is incredibly useful. It lets us narrow our search. Kepler data lets scientists estimate the fraction of stars with Earth-sized planets in habitable zones. The numbers are still being refined, but current estimates are encouraging. Some studies, 1 in 5 sun-like stars could have an Earth-sized planet in the Goldilocks zone. Other studies of red dwarfs find similar or even higher numbers. Apply that fraction to 200 billion stars in our galaxy, and the count becomes staggering. We are talking about billions of planets in the right place for life. Section 7. The Planetary Census. Billions and billions of homes. Let's put all the evidence from this act together. We've seen that our Milky Way galaxy is immense, a spinning disk of stars, 100,000 light-years across. It has been around for over 13 billion years, allowing multiple generations of stars to live, die, and enrich the cosmos with the heavy elements needed for planets and life. This galactic city is populated by at least 200 billion stars. These stars come in all shapes and sizes. Sun-like stars, the incredibly common red dwarfs. Many live for billions of years, providing the stable energy sources that life requires to evolve over long timescales. The raw materials and the power sources are abundant. Then came the planetary revolution. We now have hard evidence, based on thousands of confirmed discoveries, that planets are everywhere. The rule of thumb is at least 1 planet per star. This simple fact transforms the abstract idea of alien worlds into a concrete reality. Our galaxy is filled with 1 trillion or more planets. They are not rare curiosities. They are a standard component of star systems. The discovery of these exoplanets provides the first solid number for anyone trying to calculate the odds of life elsewhere. The number is not small. It is vast beyond any human scale of experience. The galaxy is not empty space with a few stars. It is a star field littered with worlds. Finally, we have the concept of the habitable zone. By focusing on the requirement for liquid water, we can filter this enormous planetary census down to a more manageable list of prime candidates. We look for planets that are roughly the size of Earth, as they are likely to be rocky and have enough gravity to hold an atmosphere, and we look for them in the Goldilocks zone of their star. When we apply this filter, the numbers remain astonishingly large. Even the most conservative estimates suggest there are billions of potentially habitable Earth-sized planets in our galaxy alone. Billions of worlds that have the basic requirements for life as we know it. This is the foundation of the Fermi Paradox. This is the evidence. It's not speculation. It's not a guess. It's based on decades of astronomical observation and data. We have a galaxy with billions of long-lived stars. These stars have forged the elements of life and scattered them across space. We know these stars are orbited by trillions of planets. And we have strong reason to believe that billions of these planets are in the right place at the right temperature to have liquid water. The stage is set. The ingredients are present. The cosmic ovens have been on for billions of years. So where are the bakers? This is the question we will tackle next as we move from evidence to the organized speculation of the Drake equation. Section 1. A framework for speculation. We have established the evidence. We know the galaxy is vast, ancient, and filled with trillions of planets, billions of which might be in the right place for life. The sheer numbers are overwhelming. So how do we move forward? How do we organize our thinking about the chances of finding someone else out there? In 1961, a young astronomer named Frank Drake did just that. He was preparing for a meeting on the search for extraterrestrial intelligence, and he wanted a way to structure the discussion. He jotted down a simple-looking equation. This string of letters and symbols has since become one of the most famous and controversial tools in the search for alien life. The Drake equation. It's crucial to understand what the Drake equation is and what it isn't. It is not a mathematical proof that will give us a single correct answer for the number of civilizations in our galaxy. We simply don't know the values for most of its terms. Instead, think of it as a framework for our ignorance. It's a way to break down one enormous, unanswerable question, how many civilizations are out there, into a series of smaller, more manageable, though still very difficult questions. It's a roadmap that shows us what we need to know. It separates the parts of the problem that we have good data for from the parts that are, for now, pure speculation. The equation multiplies 7 factors together. It starts with the rate of star formation in our galaxy. It then asks what fraction of those stars have planets. Next, it considers how many of those planets are suitable for life. From there, it moves into biology and sociology, asking on what fraction of those suitable planets life actually appears. Then, on what fraction of those does intelligent life evolve? Of those intelligent species, what fraction develops technology that can be detected across interstellar space? And finally, the most uncertain term of all, for how long do these civilizations continue to broadcast their existence? The result, N, is the number of detectable civilizations in the Milky Way right now. Over the next few sections, we will walk through this equation, term by term. For the first few factors, we can lean heavily on the astronomical evidence we've just discussed. We have real data and can make reasonably confident estimates. But as we move down the line, we will cross a critical boundary. We will leave the realm of astronomy and enter the realms of biology, anthropology, and even philosophy. We will be moving from evidence to speculation. The Drake equation forces us to confront what we know, what we think we know, and what is, at present, completely unknowable. It's a journey from hard science into the deepest questions about our own existence. The Drake equation begins at the source, the stars. The first term is R star. It represents the average rate at which new, potentially habitable stars form in our galaxy. Think of the Milky Way as a giant, slow-motion factory for stars. How many new machines does this factory produce each year? Astronomers look at several indicators. They study the light from distant galaxies to track star formation over cosmic time. They examine the gas and dust in our galaxy, the raw materials for stars. They use infrared telescopes to peer into stellar nurseries and count newborn stars. From all that data, we can estimate a rate. The consensus: the Milky Way's star formation has slowed over time. It was far more active in the past. Today it's producing about 1 to 3 solar masses per year. Because many stars are smaller than the Sun, that becomes several new stars per year. For the Drake equation, scientists often pick a conservative R, about 1 new star per year. It adds up over billions of years to the hundreds of billions of stars we see now. But suitable stars are the key caveat. Massive stars burn out in millions of years, likely too fast for complex life. Exclude massive O-type stars. Exclude B-type stars. Luckily, those massive stars are rare. The vast majority are Sun-like stars, and the ubiquitous red dwarfs. These long-lived stars provide stable energy for billions to trillions of years. They make up over 95% of all stars, so the overall rate is a reasonable starting point. So for R, we can confidently write down a number. Let's say 1. 1 new, potentially suitable star per year in our galaxy. That's observationally grounded. We've started the Drake equation on firm ground, the stage lights metaphor over galaxy, slow star formation montage. But, as we will see, the ground is about to get much softer under our feet. The next term in the equation is F sub p. This represents the fraction of those stars that have planets. A few decades ago, this term was a complete mystery. We only knew about the planets in our own solar system. We had no idea if other stars had planetary systems, or if our solar system was a rare fluke. Philosophers, scientists could speculate, but there was no data. All of that has changed. NASA's Kepler Space Telescope, subsequent ground-based surveys moved this term from speculation into hard observational science. We now have an answer, and the answer is astounding. Kepler's results, ground surveys, show planets are not rare. They are a normal and common outcome of star formation. The data suggests that, on average, there is at least 1 planet for every star in the galaxy. In many cases, stars have large families of planets, just like our own Sun. The fraction of stars with planets, F sub p, is therefore not a small number, not a 1 in a million chance. The data indicates that this value is close to 1. It seems that when a star forms, the disk of gas and dust left orbiting it almost inevitably coalesces to form planets. This discovery has had a profound impact on the Drake equation. If F sub p had turned out to be a very small number, say 1 in a million, the Fermi Paradox would largely dissolve. The number of potential homes for life would be so small that it would be no surprise we are alone. But the opposite is true. The universe is a profligate creator of worlds. By setting F sub p equal to 1, we are saying that for every star born in the galaxy, a new planetary system is also born. This means the 200 billion stars in our galaxy are likely accompanied by 1 trillion or more planets. The number of potential laboratories for life is enormous. This is a critical point where evidence dramatically shapes the outcome of the equation. Before the 1990s, you could easily argue that F sub p was tiny and thus the number of civilizations, n, was close to 0. Today, that argument is no longer tenable. We have the data. The galaxy is swarming with planets. So, for the second term in our equation, we can confidently write down a number. Let's be conservative and say F sub p is 0.5, meaning half of all stars have planets. Or let's be bold and say it's 1. It doesn't dramatically change the outcome because it's a high number either way. The second step of our journey is complete, and it has only magnified the paradox. Now we come to n sub e. This term represents the average number of planets per star that has planets that are suitable for life. This is where we introduce the concept of the habitable zone that we discussed earlier. We are trying to count the number of Goldilocks planets, worlds that are not too hot, not too cold, but just right for liquid water to exist on their surfaces. This term starts to narrow down the vast number of planets we just found with F sub p. We are not just looking for any planet, we are looking for planets that could, in principle, be an abode for life as we know it. This is another area where the Kepler mission has provided invaluable data. By finding thousands of planets and measuring their sizes and their orbits, we can start to get a statistical sense of how many planets are both Earth-sized and in their star's habitable zone. This is a complex calculation. The size of the habitable zone depends on the type of star, and our definition of Earth-sized can be a bit flexible. Furthermore, a planet's surface temperature depends on more than just its distance from the star. It also depends on the thickness and the composition of its atmosphere, which is something we can't yet measure for most exoplanets. Despite these difficulties, we can make an educated estimate. Various studies using different models and assumptions have tried to calculate this number. The estimates vary, but they are all surprisingly optimistic. Some analyses suggest that n sub e could be as high as 0.4 for Sun-like stars, meaning 40% of these stars could have a potentially habitable world. Other studies focusing on the more common red dwarf stars suggest similar or even higher numbers. Even if we take a more conservative estimate, say 0.1, it means that 1 in every 10 planetary systems has a world in the right place. Let's plug this in. If we have 200 billion stars, and nearly all of them have planets, and 1 in 10 of those systems has a potentially habitable world, we are left with 20 billion potential Earths in our galaxy. 20 billion. This is the result of the first 3 terms of the Drake equation, the terms that are grounded in astronomical observation. This number is the bedrock of the Fermi Paradox. The evidence tells us that there should be billions upon billions of stages where the drama of life could unfold. Up to this point, science has shown us that the galaxy ought to be fertile ground. But now, we must leave the certainty of astronomy behind. Section 5, FL, the spark of life. Here we arrive at the great dividing line, the boundary between what we can observe in the cosmos and what we only know from our one example here on Earth. The next term is FL, the fraction of habitable planets on which life actually arises. For the first time in our journey, we have no data beyond our own world. We know life arose on Earth, so FL is not 0. Beyond that, almost nothing. Is the origin of life a common, almost inevitable process given the right conditions? Or a freakishly rare accident, a 1 in a trillion shot? This is the biggest unknown in the equation. Optimists, biologists, chemists. They argue life follows planetary chemistry. Building blocks of life, amino acids, nucleic acids, found in meteorites, created easily in lab simulations of early Earth. The universe seems seeded with the necessary ingredients. Given a planet with liquid water, a stable energy source, a few 100 million years, life might be a cosmic imperative. In that view, FL could be close to 1. Nearly every habitable planet would get life. Pessimists see it differently. They say even the simplest cell is staggeringly complex. From a soup of organic molecules to a self-replicating cell to a metabolizing organism like a bacterium is a monumental jump. We still don't know how it happened on Earth. It might require a series of incredibly unlikely chemical steps. If so, FL could be infinitesimally small. So small that Earth might be the only world among billions with life. This single term could solve the Fermi Paradox. If FL is tiny, n, the number of civilizations, will be tiny too. The great cosmic silence explained, we are, for all practical purposes, alone. But we don't know. We have a data set of one, like predicting average human height from measuring only yourself. Until we can detect biosignatures, the chemical fingerprints of life, in exoplanet atmospheres, FL remains the biggest question mark. Section 6. FI, the rise of intelligence. Let's assume, for the sake of argument, that the optimists are right and life is common. Let's say that FL is high. Billions of planets in our galaxy are covered in simple microbial life. What happens next? The next term in the equation, FCI, asks what fraction of those life-bearing planets go on to develop intelligent life. This is another giant leap, and once again, we have only one data point: Earth. Here, life arose relatively quickly after the planet became habitable, perhaps 4 billion years ago. But for most of Earth's history, about 3 billion years, life remained simple. Bacteria, algae. It was only in the last 500 million years or so that complex, multicellular life exploded in diversity. And from that explosion, it took another 500 million years for one particular branch of the evolutionary tree, a branch of primates, to develop what we call intelligence. This suggests that the evolution of intelligence is not an easy or guaranteed path. There were many branches on the tree of life. Dinosaurs ruled the Earth for 150 million years, but never built radio telescopes. Sharks have been successful predators for 400 million years without developing philosophy. Intelligence, at least the kind that builds technology, seems to be a very recent and possibly fragile development. Some evolutionary biologists argue that there is no inherent drive in evolution towards intelligence. Evolution selects for traits that improve survival and reproduction in a specific environment. Bigger, faster, better camouflaged. It's possible that on most worlds where complex life evolves, it flourishes into a rich ecosystem of plants and animals that never develops high-level intelligence. The planet could be a vibrant living world, a beautiful cosmic jungle, but with no one there to ponder the stars. In this view, Fi would be a very small number. On the other hand, one could argue that intelligence is a powerful survival tool. Solve problems, create tools, communicate complex ideas. It allows a species to adapt to changing environments, not by evolving over millions of years, but by learning and innovating within a single generation. Perhaps, given enough time, the evolutionary pressure to fill every possible niche will eventually lead to the intelligence niche being filled. In this more optimistic view, Fi might be a more reasonable fraction. But like the origin of life, we have no way of knowing. We are still deep in the realm of speculation. Section 7, F-key, the will to communicate. Let's continue our optimistic journey. Imagine a planet where life arose, and after billions of years, an intelligent species evolved. The journey is not over. For that civilization to be detectable by us, it needs to do two things. It needs to develop technology. It needs to use that technology to broadcast its presence across interstellar space. This brings us to the next term in the Drake equation, FDSE. This is the transition from intelligence to a technological, communicative civilization. Is it a given that intelligence becomes technological? On Earth, humans are not the only intelligent animals. Dolphins, whales, elephants, octopuses all show signs of high intelligence. They can solve problems. They can use tools in a limited way. They can have complex social structures. Yet none have developed technology like ours. Maybe they lack physical traits, opposable thumbs, or their environments, like the ocean, make fire-based technology impossible. Many intelligent species might be philosophers or poets, not engineers. Even if they develop technology, will they use it so we can detect them? For the last century, humanity has inadvertently broadcast radio and television. We are now deliberately sending powerful, targeted signals into space. These are techno-signatures, but that might be short-lived. We are moving to fiber optics and focused transmissions that leak far less. Perhaps an advanced civilization becomes very quiet. FC forces us to consider alien psychology and sociology. Would they be curious and expansionist, or contemplative and inward-looking? Maybe they fear contact and hide, or they use technologies we can't imagine. Modulated neutrino beams, gravitational waves. FC could be close to 1, technology natural to intelligence, or FC could be near 0. Most intelligent life non-technical, quiet, or incomprehensible. With this term, we've reached the peak of our speculative climb. We have journeyed through the cosmos, from the vast star fields of the Milky Way to the mind-bending challenges of interstellar travel. We have seen how the evidence points to a galaxy teeming with planets, with billions of potential homes for life. Yet when we listen, we hear only silence. This contradiction has led to a powerful and sobering idea proposed by the economist Robin Hanson. It's called the Great Filter. The concept is a potential solution to the Fermi Paradox. It suggests that there is some barrier, some incredibly difficult step in the long chain of events from non-living matter to a galaxy-spanning super-civilization. It is a filter that eliminates almost every species that encounters it. Think of the long evolutionary and technological path we have discussed. Formation of a habitable planet. Life must arise from non-living chemistry. Simple life must then evolve into complex life. Complex life must then develop intelligence. Intelligence must then lead to technology. And finally, a technological civilization must find a way to survive for a very long time and spread out among the stars. The Great Filter hypothesis states that at least one of these steps is fantastically improbable. The silence we observe in the universe is the sound of every other potential civilization failing to pass through this filter. They are filtered out before they ever have a chance to make their presence known. The question, then, is not just, what is the filter, but also, where is it? This is the most important question for humanity. Is the Great Filter in our distant past? Or is it lurking in our near future? If the filter is behind us, it means that one of the steps we have already completed was the incredibly difficult one. Perhaps the origin of life itself is a 1 in a trillion fluke. Or maybe the leap from simple single-celled organisms to complex animal life is the barrier that almost no planet ever crosses. If this is the case, then humanity is exceptionally rare. We are one of the very few, or perhaps the only species to have won the cosmic lottery. It would mean the silence is because the universe is barren and we are alone. This is a lonely thought. The idea that we are fundamentally alone in an empty cosmos. But it is also a hopeful one. It means the danger is behind us. The path ahead is clear. We are the first, and the galaxy is ours to explore. It places a profound responsibility on our shoulders to cherish and protect the only spark of consciousness in a vast and silent universe. But there is a second, much more terrifying possibility. What if the filter is not in our past, but in our future? This would mean that the steps we have already taken, the origin of life, the evolution of intelligence, the development of technology, are actually quite common. The galaxy could be filled with young civilizations just like ours. The reason we don't hear from any advanced, older civilizations is because none of them survive for long after reaching our current stage of development. The filter lies ahead of us, a final exam that everyone fails. It could be the inevitable self-destruction through nuclear war, the unavoidable consequences of climate change, or a technological danger we haven't even discovered yet. Artificial superintelligence might replace or eliminate its creators. Mishandled nanotech could produce a gray goo consuming the biosphere, or a high-energy physics experiment could sterilize a planet. The great silence becomes a dire warning. The empty sky says the path is fraught with peril. It urges wisdom, caution, and unity, because the survival of consciousness may depend on it. Beyond the Great Filter, there are other exotic, speculative solutions to the Fermi Paradox. These ideas question our assumptions about alien civilizations. One idea, the zoo hypothesis. Advanced civilizations exist. They are aware of us. They choose not to contact us. Our solar system is set aside as a cosmic wilderness preserve, or treated like a zoo. They observe us from a distance, like animals in a reserve, letting us evolve without interference. Silence as deliberate non-intervention. A more extreme idea, the planetarium hypothesis. We aren't just observed, we might be living inside a simulation. The stars, the galaxies, everything we see, an illusion created by a super-advanced civilization. Other life simply wasn't programmed into our reality. These ideas are fascinating but unfalsifiable. No experiment can prove we aren't in a zoo or simulation. They're philosophical, not testable science, but they show how strange the answer could be. So where does this leave us? A profound mystery and a range of possibilities. Inspiring, terrifying. We may be the first and only minds in the galaxy. We may be one of many, destined to fail some future test. Or we may be the subject of an experiment beyond our comprehension. We do not have the answer. The Fermi Paradox is more than a riddle. It's a mirror. It reflects our hopes. It reflects our fears. It reflects our ignorance. It forces us to confront our place in the universe and the future of our species. We cannot afford to stop looking. The search for life, microbes on Mars, biosignatures in an exoplanet's atmosphere, a radio signal from a distant star. Every new discovery, every null result, adds a crucial piece to the puzzle. Finding life would mean the first great filter is behind us. Hearing a signal would mean the future filter is surmountable. If the silence continues, it underscores our fragility. The universe doesn't owe us sense, but we have the privilege, perhaps the duty, to try to understand it. The search continues.